section 8.2, or I think the book has listed it as 8.3. I got my numbering wrong in the notes, and I got the numbering wrong on 8.1 as well. That's why I'm labeling them 8.2 with little parentheses, 8.3. So it's 8.2 in the notes, 8.3 in the books. Sorry about the difference. We're comparing two population means, and these are called paired difference experiments. Before we start, let's talk about the different types of samples. So we have dependent samples and independent samples. Well, first, let's start with the independent samples, which was really what we did in section 8.1. So these were what we talked about last time. And samples are independent if really you wouldn't expect the results in one sample to have any impact on the results in another sample. So if I'm rolling a bunch of dice, then the dice in the first roll and the dice in the second roll, you wouldn't expect the dice to know what happened in the other roll. But furthermore, if I'm giving a test and I give a test to one group of students and give a test to the other group of students, whether the first group does poorly or not doesn't affect how the second group is going to do, because the second group is going to get whatever grade they got. If the first group didn't get enough sleep, or if the first group got bonus points or something, it doesn't affect the second group. So independent is when each sample, one sample's results outcome does not affect the other. Maybe it should be, excuse me. Okay, it does not affect the other. Dependent samples are what we're going to talk about today. So dependent samples are today's discussion. And what we mean by a dependent sample is a situation where one sample's outcome does affect the other one. So the big example that we're going to talk about are paired differences. So we're going to talk about paired differences experiments. So a sample is paired if we have some sort of like before and after, BEF, some sort of before or after, or some way of comparing two groups. So for example, if you have a bunch of people and you wanted to put them on a diet and you took their weight before the diet and their weight after the diet, that would be an example of a paired dependent sample, because you'd have two samples. One sample is their weights before, the collection of weights before, and the other is their collection of weights afterwards. But what you find is that these two groups are not unrelated, because if someone had a really large weight in the before, you'd expect their weight to be larger in the after. And if they had a small weight in the beginning, you'd expect them to have a small weight in the after. You'd expect there to be some relationship between these two things if you do a before and an after test. Well, that's exactly what we're going to talk about today. We're going to talk about a problem where we gave some students a before and after test, and we had them, the students in our problems took a pre-test, and these were their scores. I took a post-test, and these were their scores. And this definitely fits the definition of dependent. So this is definitely the description we're in, because if you think about the student who scores really high, if you get a 97 on the pre-test, you're probably also going to get a pretty high score on the post-test. It's unlikely that you're going to get an A on the pretest and then fail the post-test, right? And furthermore, the students who are really struggling on the pretest, so if you got a 52 on the pretest, moving up to a 67 is a big improvement, but you wouldn't expect the student who scored a 52 to do the same as the student who'd scored a 57. So we see some connection between this pre and this post-test here. So here's the big idea when we have paired samples. When you have paired samples, we just make one slight adjustment. So you make a column of differences. And what does that mean? You make a column right here, which is whether or not, which is the difference between the two. So we can subtract them in either order. You can subtract pre minus post, or post minus pre. It doesn't really matter. I'm going to subtract the post minus pre because I think I'll get more positive numbers that way. So I'll do 79 minus 75 and we get a 4. 67 minus 52 and get 15. That is negative 2 because their score went down. That one's also a negative 2. This one's a positive 2. The score went up by 2. and this one is 8. So here's our differences. These are basically telling us how much the scores have changed. And then what we do is we look at only the differences. Look at only the differences. Only the differences, and use the methods of chapters 6 and 7. So if we want to make a confidence interval, then we go to chapter 6 and look at how do we make confidence intervals in chapter 6? Well, we do that same list with this set of difference numbers. If we want to do a hypothesis test, we go to chapter 7 and ask how did we do a hypothesis test in chapter 7, and we do the exact same method but only with this column of differences. These two columns right here are completely ignored. So I'm going to erase them because we are not going to use them again for the rest of the problem. Okay, so let's go to this part A. Let's go to this first section where we're asked to do a hypothesis test. Well, if we're going to do a hypothesis test, there we go. If we're going to do a hypothesis test, we always do hypothesis tests using the same basic setup. And hypothesis test is chapter 7, so we're in chapter 7 right now. Then what do I need to do? Well, for hypothesis test, I need to write down my hypotheses, calculate my test statistic, find my p-value, and then draw a conclusion. So what are my hypotheses going to be? Well, my null hypothesis, I need to think about what my null hypothesis should be. Well, my null hypothesis is always ask the question of what if there's nothing going on in our study? So what if we gave a bunch of students a pre-test, did nothing, and gave them a post-test? What would you expect? Well, I would expect them to get the same score on the pre-test and the post-test. I wouldn't expect there to be any difference. And if that's the case, then I would expect this column to be a column of zeros. So my null hypothesis is that the differences are 0, because if our test did nothing, if we learned nothing from this process, 0 is what we'll get for all these differences. But my alternative hypothesis is that my students learned something between the pre and the post test. And if they learned something, then either this mu is going to be bigger, less than, or not equal to 0. Now let's think. I subtracted my 2. I subtracted the post test from the pre-test. So this student's score went up 4, and so they were a positive 4 score. So students who learned are going to, students whose scores get better will have positive numbers here. So I would put a greater than 0. By the way, when I originally subtracted them, I could have subtracted the other order. And what would have happened is I would have subtracted, them backwards, and I would have got a negative 4, negative 15, positive 2, negative 2, negative 8. That is not wrong. It's just a different way to do the problem. If I'd subtracted them in the opposite order, I would also have to change this sign and make this a less than sign because it needs to match the way I'm solving my problem. So you have to think. You can't turn off your thinking as we go through this situation. Okay. So this is our null and alternative hypothesis. Now the next thing I need to do is I need to come over and try to find my test statistic. Now back in chapter 7, you'll remember how to find a test statistic. The test statistic is, we are going to use a t-test statistic because we know what the mean is, but we have no way of knowing what the standard deviation is. So the standard deviation is not known, so we should definitely use t. So we use t. And we will go, t is x bar minus mu divided by s over the square root of n. So that's our formula way back in chapter 7. Now you'll notice I don't know a lot of these, so I have to go kind of start to figure some of these things out. So let's come right down here. Maybe in this bottom section I'll start writing the ones that I know. I know mu has to equal 0, and I know n. N is just how many samples I've got. I got 1, 2, 3, 4, 5, 6. N is 6. But x bar and s, I have to go figure those out, and I have to go put them in my computer. So I'm going to put these in Excel. So I'm going to take and put all this in Excel. Let me erase all this so I have some more space here in just a second. So I'm going to go and put these in Excel. And what I'm going to find is I'm going to find that x bar is 4.167 and s is 6.524. Let's just do 5, 2. Okay, so this is what I got from my numbers: 4.167, 6.52, and those are my numbers that I got when I calculated those out. And then mu is 0, and n is 6. All right, so now that I've got this, I'm ready to start plugging into my formula. And so my test statistic is t is equal to 4.167 minus 0. That number is 0. By the way, it's always going to be 0, so you don't even have to write it down, but I'm going to write it down. Divided by s, which is 6.524, divided by the square root of n, divided by the square root of 6. And so I put all this in my calculator, and what I get is 1.565. So hopefully you were able to get some number that looks like that. All right. Hopefully that's right. Here, I'm going to check real quick, make sure I got the right answer. Oh, hold on a second. Yeah, there we go. Good. So 1.565 is what we've got. And now what do I do with this answer? Now I have to find my p-value. And remember, for my p-value, I have to go use the app. Sorry, students, I don't have my iPad on me, so I'm going to use a pretend app. So this is, if you had your iPad, the screen would look like this. And what we do is we would put 5 up here for our, we'd put 5 up here for our degrees of freedom, because it's always 1 minus our sample size. And then we would put this in for our x. We'd put 1.6 or 565 in for x. And then you'd have to make it greater than, because what we want is we want a picture where it shades to the right. So we want our graph to shade like this to the right. If you have it less than, it'll be shading the wrong side of the graph. So make sure it's shading to the right. Make sure you've got the greater than sign. And then when you look at that, the number that should pop up is 0.089. And so that's our p-value. So our p-value is p equals 0.089. And then once we have this p-value, we're now ready to draw our conclusion. So how do we draw our conclusion? We compare this to our alpha value of 0.05. And what we see is that this 0.089 is bigger than that than alpha. So p is bigger than alpha. And then we have to kind of rack our brains and go, what does that mean? Well, what that means is that this was not a very unusual, or not unusual enough for us to say that something is wrong with our data, to say that something's up with our data. So we fail. So p is greater than alpha, so we fail to reject h naught. So the conclusion of our problem is we fail to reject h naught. And what does that mean? That means we not enough evidence, not evidence that the scores improved. However, I would tell this professor, if they gave me these numbers, I would go, you can't run off and start shouting to the hills that you've improved everyone's scores. But 0.8 is still a fairly small number, and 6 is a very, very small sample. So there's a decent chance that if you tried this again and did 60 students instead of 6, there's a decent chance that maybe this p-value would become a little bit smaller. So I would say don't give up. There's hope, but we're not ready to go run off to the publisher and put all of our results out yet. Okay, well, let's look at that last question. So the last question says, what do we do when we want to find a confidence interval? And if you remember, confidence intervals were from chapter 7, so we want a 95% confidence interval. And that was, chapter 6. And so we're really just doing the exact same thing we did in chapter 6, except we're doing it with these numbers instead of the numbers, instead of the numbers that we started the problem with. So we have these differences. Find a confidence interval with these numbers. Can we remember the confidence interval formula? Well, I can. You might have to look it up. Confidence interval formula, x bar minus TC, again, we're using T because there's no standard deviation that comes with this, minus TC times S over the square root of n is less than mu is less than x bar plus tc times s over the square root of n. And so I have to look up all of these things. I have to figure out what is x bar, what is s, what is n, and what is tc. X bar and s we found the first time in the problem. You put the numbers in Excel, and we got 4.167 here. And s we got 6.524. N is 6. It's just how many samples we had. So that's that number. And now TC, we have to go back to our app to make TC work. So here's my fake app. And now to find TC, I'm going to put my number here. And what I know I want is I want my picture to have 95% in the middle. So that means I want to have 95% right here. But since my calculator goes all the way to the left, well, I want 90% here. And since my calculator goes all the way to the left, I need to put 9.5 in for x. And then I need to make this a less than to make sure that I'm getting the right-hand side. So if I do it right, it gives me this bar and gives me this picture all the way to the left with 95%. That means if I could have stopped here, I would have had 90% in the middle and 5% on that side. All right, and so now we put this together, and I think this TC value comes out to be 2.015. So that's the number that shows in your app, and that's the number we're going to use in our calculator for TC, 2.015. All right, now that we have that, we just need to go plug everything in and start making progress on our problem. So we've got 4.167 minus 2.015 times 6.524 divided by the square root of 6 is less than mu is less than, and then we write all that again with a plus sign instead of a minus sign here. 2.015 times 6.524 over the square root of 6. Sorry about my writing. I type all this in my calculator and I get negative 1.2 is less than mu is less than 9.534. So this is what I get for my confidence interval. And hopefully this makes a little bit of sense, and this actually harmonizes with our last problem, because that means that if someone asked what this mu is, and a lot of times people put a little d on this mu d because they're saying the average of the differences. So this isn't the average of the test scores. This is the difference. This is the difference between the two test scores. So if I were to put a number line, that means if 0's here, I've got negative 1.2 and then positive 9.53. So this is the part of the number line that there's a 95% probability or 90% probability that your so there's a 90% probability that the difference is somewhere in there. So if you take the real difference between two students taking this test, 90% probability either they go from losing 1 point to gaining 9 points. So this is kind of the reasonable level of results. And notice that the possibility of not gaining or losing anything, probability being 0, is inside of our confidence interval. So that means that no change is one of the reasonable results. So we cannot reject our null hypothesis because our null hypothesis was one of the reasonable collection of results. I do believe that if you were to do the study again and make n larger, you would get a confidence interval that's smaller, and you might get a confidence interval that looks something like this, which then 0 would be outside, and so you would be able to reject. But with the data we have, with just these 6 students, we can't make those firm conclusions. All right, I hope this goes really well. This is the last section we're going to do with the confidence intervals and hypothesis tests. We're going to jump into the last chapter of the text in the next set of videos, and that's where we're going to talk about regression lines and how we come up with relationships between two variables. So good luck with that, and I will see you then.